What's going on down in the center of a white dwarf? What's it like in the middle of one of the most extreme environments in the universe? Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy and astrophysics lectures. White dwarfs are amazing objects, some of the most extreme in the universe, the end result of a dying star. They pack about a solar mass of material into something the size of Earth. Under normalish planetary and stellar conditions, over 1 million planets the size of Earth could fit inside the Sun's volume. The Sun's mass is less compact than the Earth, with the Sun weighing in at about 330,000 times the mass of the Earth. This means that white dwarfs, which pack all the Sun into a volume 1 million times smaller, are some of the most dense objects in the universe. It also means that the conditions at their cores are extraordinary and extreme. Let's see how extreme. We'll do the numbers because math or it didn't happen. We'll start with a pretty simple, nearly obvious fact. A white dwarf, where basically most stars and all planets don't change their sizes. That is, they strongly tend to not grow bigger or smaller. Now I'm ignoring the obvious large group of variable stars that do vary their radii in some way. But we can be reasonably certain that white dwarfs are not growing tendrils, turning into cubes, or oscillating and squishing in some large fraction of their sizes. To that end, we can expect white dwarfs to be spherical, since that's the most compact form of mass under self-gravity. For it to be stable, this self-gravitation must be exactly balanced by some supporting pressure. This pressure, in the Sun as well as Earth, is created by the interaction of atoms, molecules, and ions. They continually collide with each other, and the characteristics of these collisions depend on many things, but we can usually describe a type of gas, or solid for the case of a planet, with large macroscopic equations that greatly generalize all the particulars into bulk parameters. Rather than look at the individual electric field shapes and strengths of each type of ion or atom, we describe the situation with general variables like temperature and density and chemical potential. The upshot of this is the simplifying idea that there must be some macroscopic description of the star's matter's gas pressure, which exactly balances the self-gravitation. The thing is that gravity in the classical sense is pretty elementary. Mass in a volume pulls on itself with the simple Newtonian equation we all know and love. But the pressure is dependent on many, many things. To help us get a handle on the needed physics that comprises the pressure, we'll need to estimate the bulk parameters with large bulk scale values. We take our first example with the Sun. What is a good estimate for the pressure that must be down in the core of the Sun to support all its 330,000 Earth masses? We'll use some elementary physics to help us answer this. On the right-hand side of the slide, we see 4 equations. The top 2 are familiar from stellar structure. The dMdr equation is called the mass conservation equation. Basically, it says there are no big gaps with no masses in the star. This equation describes how much mass is contained within a spherical shell at a specific radius inside a star. Importantly, the density, ρ, is likely a complicated function of radius and is usually computed numerically as part of a stellar structure model. The second is the equation of hydrostatic equilibrium. I know it has hydro in it, but there is no water in the core of the Sun or any other star. Hydrostatic equilibrium here again is basically saying at every radial distance of the star, what is the pressure pushing up against gravity such that there is no net flow up or down. This depends on the mass enclosed in that radial shell and the density at that location. It is a negative sign because the pressure must decrease with greater radius. We can combine these 2 equations to get the pressure as a function of mass fraction. Notice how the density drops out of this equation, leaving us only with a demand of how much pressure is required to hold up that much mass. We have to remember that mass here is an implied function of radius, but for this differential equation, we aren't concerned with that variable directly. Finally, in the lower right, sneaking right in there, we have some real gas physics, the ideal gas law. It relates the macroscopic variables for a volume of gas. This is the equation of state. Such equations of state are where we put all the ways the gas particles can interact. For an ideal gas, a good analogy is that all the particles are basically non-sticky billiard balls with a particular distribution of collision speeds. The shape of this distribution is called a Maxwell-Boltzmann distribution, which is a skewed bell curve, where there is an excess of fast speeds. If the temperature goes up, the average kinetic energy of the particles rise. which raises the pressure because collisions are happening more frequently. Likewise, at the same temperature or pressure, if the gas is composed of lighter particles, then there will generally be more of them at higher speeds than would be the case for heavier particles. This all goes by way of saying that the sun is well characterized by an ideal gas composed of 75% hydrogen and 25% helium in the most macroscopic and rough terms. That's the underpinning equation of state which allows us to do the following. Let's take the pressure mass differential equation and evaluate it at its total sun values. All the pressure will be assumed to be sourced from the core, and everywhere we see an M, we distribute the solar mass. We do likewise with the solar radius. Multiplying all this out and filling in the value for the solar mass and radius, as well as Newton's gravitational constant, gives an estimate of 10 to the 16th pascals. Sea level air pressure is about 10 to the 5th pascals, with the deepest part of the ocean on Earth under a pressure about 10 to the 8th pascals. The sun, therefore, in the center is under extraordinary pressure, much greater than can be created in an Earth laboratory without a tokamak accelerator. But even under these amazing conditions, the ionized plasma that makes up the core still behaves mostly like an ideal gas, or at least it's a decent approximation even under such immense pressure. Now we can do the same exercise for a white dwarf. A typical white dwarf will also be about a solar mass, but the radius is now only 1% that of the sun. This spikes the core pressure up to about 10 to the 24th pascals, or 100 million times that in the center of the sun. This is a catastrophically large number. It seriously calls into question what the equation of state of matter is under these pressures. Can it possibly still be the ideal gas law? The high pressure means a high density. Do the particles in this plasma really have the space to equal out into a Maxwell-Boltzmann distribution of speeds? Is it possible that the collisions aren't fully randomized? So how close are all the particles in a core of a white dwarf, which, by the way, is composed almost purely of ionized carbon and oxygen nuclei and their free electrons swimming about? Let's see if we can do a better estimate of the central pressure of a white dwarf. Let's now go back to the hydrostatic equilibrium equation and remember that this is a differential equation which is designed to be integrated from the core to the surface. To do so, we need some way around the complicated non-analytic expression of the density as a function of radius. We therefore make the initial, extraordinarily bad assumption of a constant density. Why? So we don't have to plug all this into a computer just to get some answer. We start with this brutal, obviously incorrect simplification just to get us in the ballpark. When we do that, now we can substitute the mass of the star for its spherical volume times this odd constant density. On the right, we end up with some constants times the square of the density times the radius of the current shell of integration. This allows us to integrate the equation to get a pressure as a function of radius. The little r gives the pressure at some radius, and the big R is where the pressure goes to zero at the star surface. Setting little r to 0 to represent the core, we now have a better approximation than our previous dimensional analysis order of magnitude back of the envelope calculation. Here, our physical inputs for the density squared are 1 solar mass in 0.01 solar radius, times the square of that radius. Chugging that into a calculator gives just under 4 times 10 to the 22nd pascals, or 1.4 million times the solar core pressure. This is more accurate than the previous estimate because it takes into account the growing amount of mass contained within each onion skin layer in the star. Even better calculations and estimates would rely on knowing the state of matter, so we could do more than just a constant density idea. Now, let's do something similar for the central temperature. From my previous video on stellar structure and energy transport, we saw a bunch of differential equations relating the temperature gradient to various processes. For our current idea, let's pretend that the core of a white dwarf is somehow analogous to the core of the sun. The way energy is transported in the sun's core is through radiative transfer. Convection doesn't play a part in the core of the sun, and conduction doesn't either. So it's a demi-logical first thought, and let's try estimating the central temperature assuming energy is transferred predominantly from the core by random walk of photons. To describe this equation, we have to obtain the luminosity L at a given radius r. This involves the density, rho, the photon distribution's temperature, T, and the opacity to those photons traveling through the medium, kappa. A and C are the Stefan Boltzmann constant and the speed of light. Integrating from the core to the surface, we assume two things. The temperature at the surface is significantly lower than the core, and we again use an unrealistic average density, rho. The kappa bar is the opacity of the material to the passage of light. It's called the Rosalind mean opacity. The principal contribution to opacity is electron scattering, and to a lesser extent, Bremsstrahlung absorption. Again, putting values in known for the white dwarf radii and measured luminosities gives a rough estimate of about 80 million Kelvin. This is much hotter than the sun's core. This would be hot enough for nuclear fusion to occur in the core of a white dwarf. However, this would generate a lot of energy, raising the luminosity of the white dwarf further. So somehow, the high temperature is not inducing fusion. First, we know these to be the end states of stars, both in theory and in observation, so we know that all H, hydrogen, and helium are depleted. Carbon and oxygen, and to a lesser extent neon and magnesium, are not undergoing fusion because the temperature is simply not high enough to overcome the electrostatic repulsion of these heavy nuclei. Now that we've gotten a feel for the core's conditions, we come back to the original question. What is holding up a white dwarf from collapsing entirely? Let's use these conditions to check some stuff. If the average density of Sirius B is 3 billion kilograms per cubic meter, and the mass of a proton-electron pair is about 1 2/3 times 10 to the minus 17th kilograms, that's really small, then the number of proton and electron pairs in a white dwarf is about 2 times 10 to the 30th per cubic centimeter. Assuming everyone's all nice and lined up in a cubic formation, there are about 10 billion electrons in one row a centimeter long. This might not sound like a lot, but the fact is that the Bohr radius for a hydrogen atom is about twice their interelectron spacing. That means that if a hydrogen atom were to exist in this environment, every electron would actually be just as close to the next proton over as it would be to its own proton. That basically means that no atoms can possibly exist under these conditions. They're just packed way too tight. So now we have a bit of understanding about the conditions the matter is under, what kind of equation of state applies. How do the temperature, density, and pressure all really relate to each other? How does the white dwarf support itself? A fundamental property of the ideal gas law is the relatively straightforward linear relationship between these three macroscopic variables. It assumes the internal energy is free to distribute between heat, energy density, potential energy, and kinetic energy. But the conditions in the center of white dwarf preclude the truly free expansion of the volume, and the interparticle spacing is so tight that a bubble of a different temperature should be smoothed out instantly. Also, where can a proton or an electron go under these conditions? The equipartition of energy implied by this law seems suspect. The ideal gas law is measured originally under Earth laboratory conditions, so it's not obvious a priori that it applies in a white dwarf. But let's give it the old college try. Plug and chug the temperature and density we derived previously to check the central core's pressure if it were due to the interactions governed by the ideal gas law. We see that it can't provide all the pressure. In fact, it produces only 0.5% of the needed pressure. So the center of a white dwarf cannot be described by the paradigm of an ideal gas, a bunch of little particles colliding but never interacting. We could have figured this out alone from the interparticle spacing we just saw, but here we do the numbers. Another familiar kind of pressure comes from light itself. Radiation pressure is just the energy of the ambient photon field impacting the particles that swim in it. Sigma is again the Stefan Boltzmann constant, and c is the speed of light. Knowing the high temperature and plugging in all the known constants, we see that the radiation pressure does an even worse job than the ideal gas law in our understanding of what supports a white dwarf from collapse. With these two general laws failing, and by implication so many other equations of state that rely on atomic physics also fail, we are now forced to think of new physics to help understand these amazing stars. Because the particles, and specifically the electrons, are at 80 million Kelvin, their implied thermal speeds are 12 to 16% that of the speed of light. Also, with their compact spacing of 10 electrons per nanometer, we are no longer under the normal classical gas realm. Clearly, with these high densities and speeds, we need to take into account quantum mechanical effects. This is electron degeneracy, and we'll talk about it next time. If you like this lecture, please give it a like and share it around, and stick around for the next one when we talk about electron degeneracy. See you soon.